welcome to the video lecture series on Chemical Engineering Thermodynamics 2. Myself, Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 1, which is a phase equilibria. So in this lecture, we are going to calculate various numericals. So let's calculate this numerical. The vapor pressure of acetone and acetonitrile can be evaluated by the following Antoine equation, and Antoine equation given like this. Then assuming ideal solution, x1 and y1 at 327 Kelvin and 65 kilopascal, we have to find out the value of x1 and y1. So this is one different type of numerical comparatively previous two numerical, and we have to find out the value of p and y1 at 327 Kelvin, and value of x1 is a 0.4. So let's suppose for the case 1, given data is temperature, which is 327 Kelvin, and pressure 55 kilopascal. So first we have to find out value of P1 and P2 using this Antoine equation by putting value of temperature 3 to 7 Kelvin. So if we are going to put value of 3 to 7 Kelvin instead of this T, we will get value of P1 and P2. So this value becomes P1 is equal to 85.25 kilopascal, and P2 which becomes 39.3094 kilopascal. So this becomes our P1 and P2 using this Antoine equation. Now if we want to find out the value of P, we have to use bubble point calculation equation, or we can also go for the dew point calculation equation. But bubble point equation is much easy than comparatively dew point equation. So we are calculating this numerical using bubble point equation. So bubble point equation that can be given by P is equal to summation of xi pi saturated. So this equation becomes P is equal to x1 P1 saturated plus x2 P2 saturated. Now here becomes two unknown variable. We know that value of P, P1 and P2, but here there is a two unknown variable. So we cannot calculate from one equation two unknown variable. So we have to make this equation by the one unknown variable by changing this x2 with 1 minus x1, because we know that x1 plus x2 is equal to 1. So if we are making subject to x2, then it becomes 1 minus x1. So replacing this x2 with 1 minus x1, we can get only one unknown variable. So can easily calculate this equation. So this equation becomes P is equal to x1 P1 saturated plus 1 minus x1 into P2 S2 saturated. Now calculating this term, we know the pressure. So value of pressure is given in statement is a 65 kilopascal is equal to value of x1 we have to find out, then value of P1 which already find, which is a 85.25. So 85.25 plus 1 minus value of x1 we have to find it, and value of P2 which is a 39.3094. So rearranging this equation, we will get 65 is equal to 45.86 x1 plus 39.3094. Now again rearranging this equation, we will get 45.86 x1 is equal to 25.6906. By calculating again this term, we will get value of x1 which becomes 0.56. So this is our answer for this case 1. Now we also have to find out value of y1. So using route flow equation for component 1, that can be given by y1 p is equal to x1 p1 saturated. So using value of x1 p and p1 saturated, by making subject of y1, we will make equation x1 p1 saturated upon p. Value of x1 is a 0.56 multiplied by value of p1, which is a 85.25. So writing 85.25 here upon the total pressure. Value of total pressure, v value of total pressure, which already given in statement, which is a 65 kilopascal. So multiplying this term, we will get value of y1, which becomes 0.73. So this becomes our answer, x1 and y1 for this case 1. Now let again calculate for the case 2. For case 2, given that find out P and Y1 at 327 Kelvin temperature and X1 is equal to zero point 0.4. So here value of X1 is a 0.4 and told that we have to find out P and Y1. We have to find out value of P and y1. Temperature is also given. Temperature given that 327 Kelvin. In case 1 also 327 Kelvin. So we can directly use value of P1, P2. Okay. So here temperature is a 327. Same as the previous case. So we can directly get the value of P1s, P2s and P3s from the previous case. So value of P1s, that can be given by 85.25 kilopascal. 85.25 kilopascal. Then value of P2, which is a 39.3094 kilopascal. So 39.3094 kilopascal. And there is a no P3, only there is a 2 component. So we do not need the this P3s. So in case 2, value of x1 is given. So we have to use bubble point equation, that can be given by P is equal to summation of xi pi saturated. For 2 components, this equation becomes x1 p1 saturated plus x2 p2 saturated. Now value of x1 is a 0.4. So can say that P is equal to 0.4 multiplied by value of P1. So value of P1, which is a 85.25 plus for the x2, we have to calculate x2. Here x1 is a 0.4, so can directly say that x2 is a 0.6, because we know that x2 that can be given by 1 minus x1. So 1 minus 0.4, which makes 0.6, and P2 which already find, which is a 39.3094. So 39.3094 multiplying with the 0.6. So by calculating this term, we will get value of P, which becomes 57.68 kilopascal. Now again using the route flow for find out the value of y1 for component 1, if we are going to apply route flow, then it's expressed by y1 p is equal to x1 p1 saturated, making y1 as a subject because we want to find value of y1, so making y1 as a subject. So this equation becomes x1 p1 saturated upon p. So value of x1, which is a 0.4 multiplied by value of p1, which is a 85.25. So let's write 85.25 here, divide by total pressure that already find in this session, which is a 57.68 kilopascal. By calculating this term, we will get value of y1, and that becomes 0.59. So here value of P, which becomes our answer number 1 for this case 2, and we have to find out y1, so this becomes our answer number 2 for this case 2. So again let's revise this numerical. In statement given that the vapor pressure of acetone and acetonitrile can be evaluated by the following Antony equation. Antony equation is given. So in statement told that assuming ideal solution, so we can use Raoult's law for that. Then told that there will be two cases. In case 1, x1 and y1 we have to find using the value of temperature and pressure. So using the value of temperature in this Antony equation, we can calculate P1 and P2 by just making value of T or putting the value of T in this equation, in this both equation, and taking antilog both sides. So we will get the value of P1 and P2, which becomes 85.25 kilopascal and 39.3094 kilopascal. Then using bubble point equation, P is equal to summation of xi pi saturated. Here two components given. Component 1 is the acetone and component 2 is the acetonitrile. So this bubble point equation becomes like this. Now we are choosing this equation because it is relatively easy compared to the dew point equation. We can also use dew point equation to find out the value of P, because dew point equation that also can be given by P is equal to 1 upon summation of yi pi saturated. Okay, so if we are applying for two components, so this becomes yi upon P1 plus y2 upon P2. Then this y2 becomes 1 minus y1, and we have to solve this equation for the y1 and we will get the value of y1. But here we are going to use bubble point equation because it's relatively easy compared to the dew point equation. So if we are going to use this bubble point equation, P is equal to x1 P1 saturated plus x2 P2 saturated. But in this equation there will be a two unknown variable, so we cannot find the value of two unknown variable using one equation. So we have to replace this second unknown variable with known variable. So we can easily replace this x2 with 1 minus x1, because we know that x2 is equal to 1 minus x1, because x1 plus x2 is equal to 1. So x2 is equal to 1 minus x1. So replacing this x2 with 1 minus x1, again putting all the value and calculating this all stuff, we will get the value of x1, which is a 0.56. Then again step 2, which is we have to apply the Raoult's law to find out the vapor phase composition. So applying Raoult's law for the component 1 and get the value for the y1 by calculating this all stuff which we already find in this session. So now let's discuss about second case. In second case told that we have to find out the value of P and y1, which already easy and calculate many times in previous some numerical, where value of P1 and P2 is the same because temperature is the same. So here in case 2 told that the temperature 227, and here in case 1 there is also 327 temperatures. So this value of P1 and P2 is the same for case 2. So by taking the value of P1 and P2 from the case 1, applying bubble point equation, because here told that there is a x1. So if we have x1, we have to use the bubble point equation. Using this bubble point equation, find the total pressure, which is of 57.68 kilopascal. Using the Raoult's law and applying this pressure value in this Raoult's law, we will get the mole fraction of vapor phase component of component A, or can say that component 1. So we will get the value of y1, which is a 0.59. So this is all about today's lecture. I am completing my lecture here. Thank you.